All right, welcome back, everyone. The last week of the course. We'll try to squeeze in a lot these last couple of days and hopefully get a lot of your questions answered. Keep them coming. So, yeah, the questions live, throw them in the chat. As always, shoot me an email after the fact, however you want to do this. I threw in a couple of bonus slides that if you downloaded the PDFs a while ago, you might want to get the new ones. So this first one is a good place to start with that. I wanted to make sure that to clarify a couple of things that we talked about specifically related to hysteresis loops and Rayleigh measurements and that sort of thing from last time. So before we get back into Heckman diagrams and coupled properties, I just wanted to talk a little bit more about the polarization versus field hysteresis loops and point out that even though these are they don't directly have time in the on the axes here, you're really just measuring charge density polarization versus electric field. You can learn a lot about the dynamics of what's happening in the material from these. We talked about that a little bit last time, but I wanted to clarify a couple of things. And in particular, how do you separate out the mobile charges that are just leakage from the actual spontaneous polarization, so displacement charge from the structure of the material switching? And this gets back to a question that was asked last time about, yeah, how do you differentiate those? I talked about the PUND approach, so PUND. That is one measurement technique to help quantify what's going on. Even if you don't go to the lengths of making the PUND measurement yourself, a lot of this you can do just reading someone else's paper with their data and recognize some red flags in their measurements about what might be happening. So, for example, if you have a material with a lot of mobile charges, even as you remove the field, so you'll notice in this case, we get to a maximum electric field somewhere around here. And even as we remove the field and go back down in field, we're still seeing an increase in polarization if we follow that green line. And that's a characteristic that you often see. It's a fingerprint of leaky charges, mobile charges moving around rather than the actual spontaneous polarization that's built into the material. So when you have an actual ferroelectric measurement, so you're really measuring displacement charge from flipping dipoles, what you should see is a sharp point of some sort, where when you remove the field, then things start to switch back the other direction. So the polarization will reduce in some way. And so you don't necessarily see a fully saturated hysteresis loop all of the time, because maybe you're somewhere inside of that loop and you haven't gotten to full saturation. You should still see a maximum in polarization where you see the maximum in field. And if you deviate from that, then there's a pretty good suggestion that you're just seeing mobile charges. One great example of this, so Jim Scott published a paper where figure one actually included a picture of a banana. So this is one of my favorite papers ever. Jim was kind of a jerk at times, and he used this to call out some people in the literature about mistaken claims of ferroelectricity. So even if he was kind of harsh at times, he was generally right. So this is an example where they actually measured the hysteresis loop of a banana peel and showed that you could get loops that look like what people in the literature were claiming as being ferroelectric, because, oh, look, they could measure a coercive field, they could measure remnant polarization. And because those are zero, this has to be ferroelectric. Well, no, in this case, they're just measuring mobile charges. There's no actual saturation. And so the reason he picked a banana is because there's a class of materials, barium sodium niobate, that a lot of people refer to as bananas, just because of the chemistry. Anyway, just wanted to point that out as an example of making sure that you're interpreting the polarization versus hysteresis loops appropriately. All right, so now we can get back. Any questions on that? All right, if not, we will get back to the Heckman diagrams. And again, this is really just a shortcut to represent what's happening, whether you like it or not. You've got coupling between a bunch of different characteristics and a bunch of different properties in your materials, because the materials that we care about that are piezoelectric and or are ferroelectric are also pyroelectric, and they show an electrocaloric response and all of these other things. So um, we walked through this briefly last time. I just want to do another quick example and show you different representations of these kinds of triangles. So this is the exact same thing, just simplified. So instead of showing the words, these are the common letters that are used to represent the symbols that are used to represent these different phenomena and characteristics. So for example, we've got heat capacity, either inverse heat capacity or direct heat capacity. Alpha, the linear thermal expansion. We've already seen the D coefficients for piezoelectricity, and here's kappa, which is also epsilon r, the relative permittivity, dielectric constant, that sort of thing. So this is just walking through what some of those are, so that you know what to look for when you see these. Again, feel free to jump in with questions if the Heckman diagram is confusing to anyone. Wanted to show one example here of how this is important. I mentioned last time how one of the beauties of this diagram is that you can show how you can combine different measurements to get to something and get a value for a phenomenon that you may not be able to measure directly, or may be very difficult to measure directly. That's what I find to be the most useful about this. The other part is don't overlook these secondary contributions if you're making measurements. If you're trying to take advantage of a certain property of a material, don't forget that you're probably getting contributions from other aspects that you may not even realize. So this is one example for if we're coupling between temperature and displacement. So in this case, D is basically the same thing as polarization. dP/dt or dD/dt, the change in polarization with temperature, that's just the pyroelectric effect. So we've already described that one. It's the amount of spontaneous polarization, how much the spontaneous polarization changes as we change temperature. There's a primary contribution to it, which is this dark line here. That's just the direct, because crystallographically we have a change in polarization when we change temperature. That's what we were describing. So the primary contribution is that when we have constant strain. So that means that when there is no strain, this is what we measure as the pyroelectric coefficient. However, how often do you have a material that has exactly zero strain? How often do you have a zero strain when you change temperature? How often do you have a scenario where it's possible to maintain completely zero strain as you're changing temperature? That's difficult to do. Thermal expansion is always present. And so you're also going to get a secondary contribution, which is the change in displacement or polarization with strain, as well as the change in strain with temperature. So that means that you've got these two contributions. So you change in strain with temperature, that's thermal expansion. And then the change in strain with polarization, that is a type of piezoelectricity. So not the D coefficients that we've been talking about, but it's an E coefficient, which is directly linking strain and polarization. And so in order to capture the entire pyroelectric response at a constant stress, so constant stress is relatively easy, you just don't touch it. And so the easiest way to keep materials unstressed is to have that stress be zero. It's possible to try and have a constant stress in some other manner if you've got a clamp on it of some sort where you can maintain that. But it's way easier just to make that constant stress zero. So when you have constant stress, there's going to be these two different contributions. One is the direct response at constant strain, and the other is going to be the thermal expansion plus piezoelectric contribution, and these add together. Most of the phenomena that we talk about related to the Heckman diagram. So if we're talking about piezoelectricity at constant stress or strain, or constant field, or constant voltage, or any of these kinds of scenarios, most of the time, what ends up being the primary one will constitute something like 90 or 95 or even 99% of the overall. For pyroelectricity, though, and part of the reason that it is a common example of this, these are essentially the same magnitude. So half of your pyroelectric coefficient comes from that primary, so the actual, the direct pyroelectric response, which is this one. And then the other half really comes from the coupling of thermal expansion coefficient plus the piezo response. And so depending on your boundary conditions, you might get a factor of 2 difference in the measurement, whether you're enabling both of these or not. So hopefully that makes sense. It's really a matter of just keep this in the back of your mind that the boundary conditions matter. So if you're measuring at constant stress, constant strain, constant temperature, or if all of these are changing at once, you need to be able to put together the pieces of the puzzle that are contributing to the overall total. All right, hopefully that makes sense. Let's think briefly though about what it means for each of these kinds of parameters to be held constant. So I mentioned stress. Stress is one. The easiest way to hold stress constant is for stress to be 0. And the easiest way to let stress be 0 is just to leave it alone, not touch the sample, and not have it clamped to anything else. So we often refer to 0 stress state as free, and 0 strain as clamped. So 0 strain means essentially I've glued this thing to something else that's way stiffer than it so that it cannot move. That's the conceptual way to think about it. But how effective is that going to be, especially for a bunch of ceramics that are really stiff to begin with? How do you make sure that that strain stays exactly 0? Because if you, let's say, glue it to something, you've got a thin film that you glue to a substrate, you can still get bending. Let's say you can still get bending of a beam if the even if the strain on the thin layer on top of it is small compared to everything else. So it's really hard to have exactly 0 strain. It's a little bit easier to have 0 stress just by letting things deform as they choose. Similarly, maintaining a constant entropy is really hard to do. Maintaining a constant temperature, that's a little bit easier, at least relatively easier. So that's another way of approaching these. So what about constant field versus constant polarization or constant displacement? So constant field, the easiest way to maintain a constant field is for that field to be 0. So the easiest way to do that is that we short circuit the sample. So if we have a miscellaneous sample that has electrodes on it, if it's short circuited, we just tie those 2 electrodes together so that any charges that develop cancel each other out, and you end up with 0 field accumulated. That's short circuit is constant field. It's open circuit is going to be the rough equivalent, so constant polarization or constant displacement. But that means that for that to stay constant, you're going to end up developing a field, and because of that field effect, you're going to get a lot of secondary effects from all of the other contributions on this triangle. So hopefully that terminology makes a little bit of sense. When we talk about free and clamped, we're really talking about free being 0 stress, clamped being 0 strain. Short circuit is going to be a constant field, which is 0. Open circuit is going to be constant polarization. Isothermal is when we're going to hold temperature constant. Isobaric is constant entropy. That's really hard. If any of you remember back to when you took some version of a thermo class at some point, whether you learned about the Carnot cycle or you learned about it from a materials thermo perspective, how do we usually talk about isobaric conditions? Or sorry, isobaric would be pressure. But if you think about it from a heat capacity or an entropy perspective, easiest way to do that is make it really, really fast. So we can do the same thing with these guys. So if we're making a piezoelectric measurement, for example, we can change the measurement frequency. And if we go fast enough, then the material doesn't have time to respond. So if you think back to our polarization mechanisms, if we go really, really fast, then the material doesn't have time to respond, and that can be equivalent to, or at least a proxy for, a zero strain response. And if we go slowly, then that can be, it's free, and the material can respond quickly, or can respond more quickly than the driving force that we're applying. And that's going to be similar to constant stress. So we can, that's one of the simple examples of how we can approach dealing with these. So of course, because we're complicating things, don't forget about anisotropy. So we talked way earlier in the class about direction dependence and the anisotropy of each individual crystal structure, and then expanding that to, once we have applied a poling field to a piezoelectric, then we've induced anisotropy there. So you can add direction dependence to all of these, and all it does is just make things more tedious and increase the size of the matrix that we have to deal with. But that's just to keep that in the back of your mind, that all of these are going to be direction dependent as well as boundary condition dependent. All right, so I sort of walked through a few of these already, but as just to give you some more examples of why this matters and how we might end up using it. When we're talking about permittivity, if we're measuring permittivity, there's going to be a contribution from a constant strain, and then there's going to be another contribution from constant stress. And if you go through, you can set up equations associated with these. All this entire diagram just comes from free energy expansion, Landau equations. You can go back and derive those if you feel like it, or look them up in Nye. But the part that I want to point out is that if you measure constant strain permittivity and you measure constant stress permittivity, then the difference between those two is going to be related to the piezoelectric response and the stiffness, as long as you keep temperature constant. And so if you walk yourself around this diagram, hopefully that ends up making sense. If you go through the tedium of deriving the equations, you can get to the same point. I find it a heck of a lot easier just to drive around the diagram and say, if I'm measuring a permittivity at constant strain, that means that I'm measuring something fast, really high frequency. At constant stress, it's going to be a lower frequency. And so if I just do a frequency sweep of permittivity and say, here's what the value is at high frequency, here's what the value is at low frequency, and now I can get a feel for what the stiffness and the piezoelectric responses are. So because these are all multiplied together, I can't make a single measurement and get all of the rest of them. But if I'm able to measure stiffness separately under constant field, so if I measure the stiffness with it when the sample is short-circuited, and then measure the permittivity, I can get the piezoelectric coefficients from that. So that's another useful example. I've also got open versus short-circuit compliance on here. So compliance is just inverse of stiffness, so that's how squishy the material is. So if I can measure the elastic response of something under a short circuit condition and then under an open circuit condition, the difference between those will tell me something about the piezoelectric response. That makes sense because the whole idea of piezoelectricity is coupling between electrical and mechanical responses. And that beta that's in there is the stiffness at constant stress. So same thing with thermal expansion coefficient. Because when I heat something up and it changes strain, it changes volume, then that volume is going to, in a piezoelectric material, is going to induce an electric field. Then by measuring the thermal expansion coefficient under short circuit conditions versus open circuit conditions, I'm going to get a different value. And the differences in those two values relate to the pyroelectric coefficient, the piezo response, and the stiffness. So hopefully that's explains why we need to care about these things and recognize that the boundary conditions are important, because we can get very different values when we make these measurements. If you're building a device that depends upon any of these characteristics, so piezoelectricity, thermal expansion, pyroelectric response, any of these, just know that the boundary conditions where it operates will give you different values. So, any additional questions on Heckman? want to wrap that up with another example of how this plays out for piezoelectricity. So you can imagine one way of making a piezoelectric measurement is really just to squeeze on the material and measure the charge that comes out of it. That is what's known as a Berlincourt meter. It's very simple, very easy. It's not very precise. You can get values from that kind of a measurement that may vary by 5 or 10 or even more percent from one day to the next. So Berlincourt measurements are simple. They're not super precise, but resonance measurements are the IEEE standard for a reason. And the way that those work is really just what we just showed. So you apply an electric field to your sample and watch it strain. You're not actually measuring the strain. You're just applying an electric field and seeing the electrical response. So because the material is piezoelectric, you're going to get a coupling between that mechanical resonance and the electrical response. And in this case, this figure is from Jaffe. They're plotting it as reactance. On the next slide, you'll see it where it's plotted as impedance, which is a little bit more common these days. But the point is that if you have a non-piezoelectric capacitor, that reactance is going to gradually increase and sort of saturate. And if you have a piezoelectric response, there's going to be a resonance that corresponds to the mechanical resonance of the material. And from that mechanical resonance, the difference in the frequencies between the resonant frequency right here and the anti-resonant frequency, then you can back out what the piezoelectric characteristics of the material are. I mean, it just comes down to representing the sample as a in this circuit. So when we do this in the lab, this makes for a very, very simple and very quick and easy and still very precise measurement of the piezo response. So we can take our sample and stick it on an impedance analyzer, do a frequency sweep, and we see this resonance behavior. And that just by looking at those two frequencies, we can calculate what the coupling coefficient of the material is. So how good it is at coupling between electrical and mechanical energy. So the width of this, the bandwidth of this also tells us about the quality factor. So how much energy is being dissipated and how much is being converted. And then if we know anything at all about the stiffness, we can calculate the piezoelectric coefficient. So from this, we can measure permittivity above and below and above the resonant frequency, and we can get information about the piezoelectric response directly from a purely electrical measurement, which is way simpler than actually trying to measure strain. Because remember, even for the best piezoelectric materials, we're talking about hundreds of picometers per volt. So if we're applying 1,000 volts, we're still only getting nanometers of displacement. So measuring nanometers of displacement can be difficult. But making this impedance measurement and seeing the resonance and anti-resonance peaks, that's pretty straightforward. All right, so another example of this. So again, just a picture of an impedance measurement where you get a resonant frequency and then an anti-resonant frequency. And from that, we back out. And what this is showing is that when we're looking at the impedance itself, the reason for this resonance is that we've got a capacitive portion above and below the resonance, and in between, from a circuit perspective, it's looking like an inductor. But from that simple measurement, just the anti-resonance, the resonant frequencies, we can get the coupling coefficient directly. And then if we know anything at all about the strain or the permittivity or the other characteristics, then we can plug those into the other equations and pull out the piezoelectric coefficients along the way. And the appendix in Jaffe has the IEEE standard from whenever the Jaffe book came out. I think it was in the 70s. The IEEE standard has been updated slightly to account for a few different kinds of materials and different geometries and things like that, but the basics are still the same. It all comes down to being able to make these kind of measurements. So one other thing that I wanted to point out on this slide, you'll notice there's another blip right here at lower frequencies. If we kept going higher, you'd see others that are showing up. So you can get multiple different harmonics from these. So if you remember, the whole reason that we see this electrical resonance is because there's actually a mechanical resonance in the sample. So just like a tuning fork, there's a natural resonant frequency based on the geometry of the sample. And so we will actually get, so it's basically a wave, and then we'll also get a wave at, well, sorry, apologies for my artwork, but pretend that is a second harmonic. So we have a wave that's half the wavelength, and another wave that's half the wavelength of that. And so we'll get harmonics at each one of these. And so you can use that to help identify if there are other modes. So for one, if we really want to know this 3 mode, so we're measuring in the direction of the applied field, that's great. We can measure the geometry, know what the wavelength should be from stiffness and these kinds of things. But keep in mind that when we apply a field along that direction, we're also, because of Poisson's ratio, going to get strain laterally. And those lateral vibrational motions are also going to resonate. And so we're going to get vibrational modes in every possible direction from this geometry. So if you really want to complicate things, you make your sample in a very simple geometry where you've got multiple different resonant modes that are all going to overlap. If you want to make life easier on yourself, you create a sample geometry that doesn't support direct modes in the lateral direction. So for example, if you want to measure this E33 and avoid complicating modes from the side, you could make this not a perfect rectangle, but maybe make it a prism of some sort, so that the thickness or the width changes as the length changes, so that you don't have a one cohesive resonant mode in this direction. But you'd also want to do the same thing in that direction. Because if you have a constant cross section in either of those, you're going to get resonant modes that come in from that. So one example where this comes into play is these kinds of resonators, these piezoelectric resonators, are what serve as electromechanical filters in your cell phone. If you look at the resonators that are in the phone, they are irregular pentagons from the top, because they want to take advantage of the resonance through thickness, which it gives you the highest frequency. So it's meant to be a thickness arrow. But avoid any of these spurious contributions from lateral modes. And so the easiest way to do that is to make a shape that doesn't allow easy bouncing of these lateral modes in an acoustic perspective. All right, so here's an example of what one of these impedance sweeps might look like when you have additional modes involved. So the primary mode that we care about is this one, but on top of that, we've got contributions from lateral modes. It could be radial, it could be a square mode. I don't know what the shape of the material was. I guess in here it's shown that it's a thin plate and disc, but if you get too many of them contributing on top of each other, you end up with a messier looking resonance spectrum that makes it harder to interpret. But you can back out what each one of these is coming from if you know the geometry. Hopefully that makes sense. But remember that the whole reason that these resonant measurements work is because of that coupling between electrical and mechanical. And by doing these resonant measurements, we can measure essentially the different pieces of the Heckman diagram that we're on. So at low frequencies, we're under a zero stress, so free condition. At high enough frequencies, we're effectively clamped, so it's not able to vibrate. So that's what's happening at this resonant mode, is that above that frequency, it can't vibrate in that at that mode anymore, because you've gone past its natural frequency. All right, so hopefully that explains why we care about Heckman diagram, why we care about impedance measurements to get electromechanical piezoelectric response. And now we can move on to learning more about other materials. So this is wrapping up the Heckman diagram component of it. And it just, as I pointed out a few times along the way, just remember that the boundary conditions matter. And so the fact that if you're trying to take advantage of electromechanical coupling by using a piezoelectric material, or take advantage of pyroelectricity, whatever it happens to be, all of the other boundary conditions are going to play into that. So make sure you know what it is that you're measuring, make sure that you know what it is that you're using in your product, and how those values might change as we go. All right, any questions before we jump into relaxers and anti-ferroelectric materials? Okay, so I've lumped together relaxer ferroelectrics and anti-ferroelectrics because they are sort of opposite ends of the spectrum, but we will, in both cases, it's the local environment around the cations that really make the phenomenon happen. And so these are different modifications of ferroelectrics. So to start off with, when we talked about ferroelectricity in the beginning, it's your crystal structure has this built-in spontaneous polarization where there's a dipole that's built right into the crystal structure. And at some point you get to there's a large enough field built up when you have enough of those dipoles smashed together that you end up with a domain wall. And so that's the basis of ferroelectricity. Anti-ferroelectricity, one way to look at it is just imagining that the size of this domain wall and the cost, the energetic cost of that domain wall is essentially zero. So instead of having an interaction between this dipole and the one next to it that says, you know, we're lower energy when we're pointing in the same direction, that interaction is just the opposite, saying that it's actually lower energy to balance things out locally. So if you have a spontaneous polarization pointing up here, then it's lower energy for the one next to it to be pointing directly down. And that means the one next to it is up and down and so on and so forth. So one way to look at this is that the domain wall energy is zero. And that means that it doesn't cost anything to create that domain wall, and therefore it's lower energy overall if you don't have any macroscopic polarization. But you'll notice in this example, you end up with essentially columns where all of the unit cells in one region are pointed up, all of them right next to it are pointed down, all of those are pointed up. And so you end up with this essentially doubling of the unit cell. So the unit cell that we use to describe what the crystal structure is at all, in a ferroelectric, we just say it's this one, and then sometimes the one next to it is pointing in the same direction, sometimes it's opposite. For anti-ferroelectricity, because we know that this periodicity extends further than just that one unit cell across the entire sample, every time you have a plus, you've got a positive, you've got a negative right next to it. So that means that from a crystallographic perspective, an anti-ferroelectric might look exactly like a ferroelectric, except the unit cell is now twice as big because it has to incorporate both the polarization pointing up and the polarization pointing down, because that's the repeat periodic unit across the entire crystal structure. So one example is one that I've shown here. One possibility is where you've got columns of these arrangements. You can imagine, this is of course in 3 dimensions. So you could also imagine that if you have those columns laid down, then if you look at it from the side, you end up with sort of diagonal periods where the way that the spontaneous polarization arranges is head to head and tail to tail everywhere. So that's another possibility. It's really hard to distinguish these from macroscopic characterization techniques. So diffraction or electrical measurements or a bunch of different other things. It is possible, but it's difficult. The magnetic community is way ahead of us in this regard in terms of nomenclature, so we just steal their nomenclature. And so there are a bunch of different types. There are different ways that you can arrange these periodicities of antipolar arrangements of these unit cells. And so that's the way that these all come together. This one is just ferroelectric, or if it's a ferromagnetic, it's ferromagnetic. But the rest of them are different examples of anti-ferroelectric, anti-ferromagnetic from this particular paper, showing you where those come into play. So what does that actually mean in terms of the properties? So now we have the same spontaneous polarization that we had in a ferroelectric, but when we look at the material macroscopically, we don't see it because everything cancels out locally, because every single component, every dipole is balanced by the one next to it. And so the net is exactly zero. That sounds a lot like an unpoled ferroelectric, and in some ways it is. It's just additional levels of order and structure and periodicity in there. But just like an unpoled ferroelectric, when we apply a large enough field, we can get all of those to align. So when we start at low fields, it looks just like a linear dielectric. And then we get to a high enough field that even though it starts like this, eventually we're going to flip everything around so that all the dipoles are pointing up. And now suddenly it looks just like a ferroelectric and behaves just like a ferroelectric. But we remove that electric field, and we know that in its baseline state, this anti-ferroelectric material really wants, it's at lowest energy when it's in this sort of configuration. So we remove that electric field, and eventually it flips back to being anti-ferroelectric. And so each individual dipole is balanced by those around it, and they all cancel out, and we go back to being nonpolar. And again, we can do the same thing in the opposite direction. And so because of that, we end up with these fun-looking doubled hysteresis loops that are really what you're doing is introducing a field-induced phase transition. So this region in here is where it's anti-ferroelectric, and each spontaneous dipole is balanced by its neighbors. But eventually you get to a high enough field, now it behaves like it's a ferroelectric. And so we can use this electric field, externally applied electric field, to change the crystallography, well, to change the phase of the material to go between an anti-ferroelectric phase and a ferroelectric phase. And then we remove the field, it goes back to its happy place being anti-ferroelectric. So that's kind of a fun looking hysteresis loop, fun phenomenon. How might we use this? There are a bunch of different potential applications. The one that gets the most attention is this is a great way to store and then discharge energy. So from a, let's say for a capacitor perspective, if you apply an electric field, the area here, that's how much energy you are actually storing and then discharging from that's proportional to the amount of energy that you're storing and then releasing from that electric field. And so for a perfectly linear dielectric with no losses, that looks like a nice and efficient, you get a large amount of energy back out. Keep in mind though, that that's on this linear portion, that's a really small amount. So the scaling on this A, B, and C plot at the bottom that I took from that the paper listed right there, the scale is off a little bit. So keep in mind that the slope of these lines, the polarization versus field, is the relative permittivity. And so that slope of that polarization versus field line tells you the relative permittivity, higher potential for energy storage. But it also goes as the electric field squared. So the higher the field you're able to get to, the more energy you can store. So from a ferroelectric phenomenological response, if we apply a field to this ferroelectric and then remove it, we've only discharged that amount that goes back to the remnant polarization. So the green portion is how much energy we've gotten back out. And the rest is still essentially stored in the material. In order to get to that rest of it, we have to go all the way back around the loop again. And then we're still only able to recover that green component. So that's the amount of polarization that is released when we release that electric field. So if we want to store energy in a capacitor and then release it quickly, ferroelectrics don't do a great job of that because it takes a lot of energy to put in to polarize everything, and then we don't get that much back out when we release it. Anti-ferroelectrics, though, because they really want to go back to being completely nonpolar in this balanced state, if we can apply electric field and get them all to point in the same direction. So remember, the relative permittivity is the slope of this P versus E curve at any point. So in this region, the effective relative permittivity is massive. And if you think back to our MLCC discussion, in order to get a large capacitance, we want a large permittivity. Well, this one is transient because it only happens while we're going through the switching process, but it soaks up a heck of a lot of charge when we do that. And so the effective relative permittivity is massive. And then when we remove that field, we're able to, the energy of the sample wants to go back to being antipolar and antiferro and back to this antipolar state. So that back switching means that we're releasing all of that energy that we stored in these dipoles. And that's why we end up with a much larger green area in this component. So from an energy storage perspective, capacitors that are based on antiferroelectrics have a really high, there's a lot of potential to store a lot of energy and be able to access that stored energy again when you remove the field by using antiferroelectrics. But keep in mind, there's a challenge here because this is a phase transition. So we are inducing a lot of, we're putting a lot of charge into the material. We're potentially inducing a lot of mechanical strain associated with that phase transition. So in order to take advantage of this, it's a balance between storing as much energy as possible, but not creating so much strain in the sample that it fractures on discharge or fatigues over many cycles. Because if you want to use a capacitor in some sort of a device, let's say that device is operating at a megahertz, then you've already hit 1 million cycles after just 1 second. So fatigue lifetime, we need things for capacitors and similar sorts of electronic components. We need cycle lives of 10 to the 9th, 10 to the 10th, sometimes 10 to the 12th cycles. For memory devices, people are looking even 10 to the 15. So that is a heck of a lot of cycles to be going through something like this, where there's a large strain and large a phase transition. So that's one of the challenges of taking advantage of this kind of approach. As an example of where this would be important, so this is the specific component that I'm showing here is a little old, but the concepts are still the same. So this is an example of a grid tie microinverter for a residential solar. So what that means is you've got a photovoltaic cell, a solar panel on top of your roof, and that's DC. So light comes in, it creates electron hole pairs. You get a DC voltage out of that solar panel. If you need to connect that to your grid is AC. And in between those two, you need what is known as a DC link capacitor. So there's a capacitor that's built in there that you want to keep the voltage on one end. So let's say this is going into a battery as shown here instead of a photovoltaic. Same concept, just inverted. So now we're going to be storing the energy instead of creating it. But we need to convert between AC and DC. And the purpose of that capacitor is to keep the voltage on one side of it completely constant, and on the other side, the current is flipping back and forth because we've got AC on one side and DC on the other, and we need to keep the energy flowing between those two. And so this is just an example from one particular application. So the values on here are representative of that particular inverter, but the concept of having a DC capacitor that can handle high voltage and high current at high frequency over decades is of huge value. So we want something that is going to cram as much capacitance as possible under these conditions into a small space as possible. And you'll notice that in at least at the time of when this inverter was made, this was from maybe 10 years ago, 8 years ago, capacitors made up about half of the volume, almost half of the cost, and half of the failures in these kinds of inverters. It's a little bit better now, but it's still much greater volume and cost and failure rate than we really want it to be. So this is an area where there's a lot of need for improvement in these capacitors. So the reason I'm bringing this up now is that at the time it was Bosch, and then it was acquired by TDK, developed an antiferroelectric based capacitor that helped with this a lot. So because of taking advantage of the antiferroelectric response of the capacitor and engineering it so that they could actually get all of this charge out, if it's keeping up, all of this charge out during discharge, then they were able to massively reduce the volume needed in those materials. And so they did this using a PZT-based system, and I'm going to come back to the PZT system again because it's just so darn flexible. So depending upon where you're sitting in the phase diagram, and we've seen this portion of the phase diagram before. So that's just the that back panel of this three-dimensional diagram is just the lead zirconate to lead titanate PZT phase diagram that we looked at earlier, and this is the morphotropic phase boundary. Now, if we start adding lanthanum, that adds even more possibilities. So we can go anywhere from having a cubic, non-ferroelectric, or even one of these other phases well below the coercive field. We can have a linear dielectric, if that's what we want. We can have a nice square hysteresis loop ferroelectric. We can, as we talked about previously, we can engineer that ferroelectric response to be a hard ferroelectric, or we can engineer it to be a soft ferroelectric that has a lot higher slope and greater permittivity and greater strain. Or now that we start to introduce anti-ferroelectric possibilities, so you'll notice down here the anti-ferroelectric orthorhombic phase of lead zirconate. If we play around in that region and we can help to stabilize that by adding lanthanum, now we have this region of anti-ferroelectric response that we can add possibilities. So we can have a very slim loop anti-ferroelectric, or we can have one that's got a little bit more width to it, depending on what application we want. And so not shown on this diagram, but stabilizing these kinds of anti-ferroelectric response, a lot of times we will add either lanthanum or niobium as a donor dopant, and we'll also add tin or hafnium, tin to stabilize the anti-ferroelectric response way down on the zirconium rich end. So this is a long way from that morphotropic phase boundary where many of the normal ferroelectric and piezoelectric applications are used. If we get much zirconium rich, then we can get this anti-ferroelectric response and take advantage of it for other applications. So just wanted to give an example here of this is also applicable in thin films. So these are some thin films that I made when I was at Sandia way back in the day, and just showing you that when you look at the energy that you can store and then discharge from these samples, you've got a normal ferroelectric here in blue, a more gradual linear looking ferroelectric that can handle a heck of a lot higher field in red, and then the green one is the anti-ferroelectric version, where if you need to operate, let's say at 500 kV per centimeter or something along those lines, then the green one gives you a heck of a lot higher energy density than the other two, because you're able to take advantage of this energy on discharge from that anti-ferroelectric switching. So as I mentioned before, lanthanum and tin are very common additives to stabilize the anti-ferroelectric response in thin films or in bulk materials. Also, niobium instead of lanthanum is another donor dopant that helps out. All right, so any questions on anti-ferroelectrics? All right, so now we're going to switch gears slightly, but still stay in that perovskite realm of what else can we do with these sort of modified ferroelectric behaviors. And so on the anti-ferroelectric end, we were sort of taking advantage of the interactions between the dipoles at the very local level, and what happens when if we want to expand that. So if we go back to looking at these polarization mechanisms that we talked about previously, and I mentioned that the vertical scaling on here is pay attention to the numbers rather than the actual geometry, because there's a huge difference between the permittivity response, the polarizability that you can get from the purely ionic polarization versus dipoles. And so if we really want to have a very high permittivity for some reason, that could be capacitors, it could be for other reasons, we want as many of these polarization mechanisms active as possible, and we want them to respond as easily as possible with few barriers. So taking advantage of these kinds of ferrodaic reactions, that's great, that's a battery. The barriers for that are not they're going to get in the way of us being able to use these quickly. So if we want to operate at high frequencies, and we want to operate these efficiently without much loss, avoiding the kinds of chemical reactions and intercalation and other behaviors of the battery are going to be important. So we're going to ignore those for these purposes, and we're going to try and focus on how do we get as much contribution from dipoles as possible, but with little barriers. So when we talked about ferroelectric switching earlier, we talked about using Rayleigh measurements and pre-stack measurements to look at barriers to polarization reversal and this kind of stuff. We want something with as reversible of a dipole contribution as possible. We want very, very little barrier to that switching. So how can we go about that? The prototype example of a relaxer ferroelectric is lead magnesium niobate, PMN. And so you'll notice in here, we start with a perovskite, and on the B site, instead of having titanium or zirconium, or both titanium and zirconium like we have with PZT, we throw in magnesium and niobium. And there are other examples of this, but PMN is the prototype for a reason. It is the best example of this. It's not necessarily the highest properties by itself, but we can engineer it, and it has a whole family of other friends that we'll talk about a little bit. But we'll start with PMN, and magnesium is a relatively for the B site. Magnesium is relatively large, so it just barely fits into the B site, that center octahedral site of the perovskite, and it's 2+, and niobium is 5+, and so that's why we need, in order to balance the charges, this B site overall needs to be 4+. And so that's why we need 2/3 of these being niobium and 1/3 of them being magnesium, so that we get charge balance. But from that, we end up with a wide variety of different local bond environments. So if you can imagine, you've got this tetrahedral site, and if you've got magnesium in one of them, and the next one over is niobium, the way that they're interacting with the 6 oxygens surrounding each of them. So this cation is going to, the bond with that oxygen is going to impact the bond with the way that oxygen bonds with the next one over, and the next one over, and the next one over. And because you have these very different sizes between the magnesium and the niobium, and you have very different charges between 2+ and 5+. And oh, by the way, we've got these huge lead cations sitting in there as well. So we have a relatively constant lead oxygen sublattice everywhere else. And then we're mixing up which B sites are filled by either magnesium or niobium. You end up with a wide range of local environments between this cation to oxygen to that cation, or this one and its next nearest neighbor over there, and that next nearest neighbor over there. And so because of that, the spring constants between each of these, so if we think back to the polarization mechanisms plot, we're looking at the ionic aspect as basically being springs, and then from that, we're developing these spontaneous dipoles. So we've got different spring constants all over the place. And if we look at the spontaneous dipole there locally, so let's go back to that octahedral model. Each one of these, the cation can sit just a little bit off center in either direction. Or if it's rhombohedral, it's going to be sitting off center in a different angle. And so the local environment, the variety of local environments, means that you've also got a wide variety of different displacements locally. And so you've got dipoles that are all over the place and are just not coherently communicating with one another. So how that manifests in terms of properties is that, well, I like this plot because it compares to barium titanate. So you'll notice we used barium titanate as the pinnacle of high permittivity, and it's shown down here. And these PMN materials just absolutely blow that away. So they've got much higher relative permittivities than barium titanate, even at barium titanate's phase transition. You'll notice that this permittivity maximum is very broad, and it's frequency dependent. So the temperature, or so the temperature where this maximum is, so if you define the phase transition as where you see that peak in permittivity, and that's not a good definition for the phase transition, but it's an easy way to measure it. the temperature where you would say this goes from being the low temperature phase, so tetragonal or rhombohedral, to the high temperature phase being cubic, for example, that temperature actually changes with measurement frequency. And so that's all of this combined is suggesting a really dynamic local environment that we basically just don't know what the heck's going on because all these ions are wiggling around in different ways. And it's not a simple, cohesive, well-behaved, well-ordered material like we see in pure ferroelectrics. So the other aspect is when we look at the dielectric loss, so tan delta, we see as we looked at before, barium titanate has peaks in its dielectric loss whenever it goes through these phase transitions. These relaxer materials have a much higher loss when they're in this disordered, messy, who knows what's going on sort of state than when they're above that permittivity max and everything collapses down. We also see a large frequency dispersion in that lower temperature region. So what's actually happening in these materials? I mentioned that PMN is the prototype, and that's the data that are shown here are all for PMN. But you can induce this kind of relaxer ferroelectric behavior in all sorts of different chemistries. The most common ones are shown here: potassium tantalate, PLZT, barium titanate. Once you start introducing additional disorder. So in barium titanate, you can get this by adding bismuth and a little bit of zirconium. Potassium tantalate, a lot of times it's done by throwing in calcium and or niobium. And so you can get disorder on the A site and or the B site with or without vacancies. There are many different ways of getting this kind of response. PMNPT is one of the strongest and certainly the most sort of the prototype. It was the original that was recognized as, wow, this is interesting new physics. The important thing here is that the disorder is really important, but I want to point out that this is not the same as the high entropy fad that has taken off across material science lately. So yes, the disorder that comes from having these different cations on different sites and all that kind of stuff, it is that disorder that eventually leads to this relaxer behavior. But this is not just, oh, we threw a bunch of different atoms on a site and magically got a new response. There's a lot more to it than that. And so happy to get into the high entropy discussion if people are interested in that space. But I don't want to spend too much time on it here other than to say that this is distinct from that high entropy stuff. This is the relaxer response is different from that. So what it boils down to is the fact that those dipoles that I was talking about, the atoms being shifted apart from exactly where they want to be in the lowest energy point because of thermal vibrations, they're going to be wiggling all over the place. That happens in every material. But in well-behaved standard ferroelectrics, those displacements are coordinated. And so the titaniums all sort of shift together, the bariums all sort of shift together, and the oxygen sublattice shifts as well. In these relaxer materials, because of all of that disorder from the different sites and the different local bond environments, those displacements are uncorrelated with one another. So the thermal energy of the materials still want to be, the ions still want to be sitting slightly off center, but the thermal energy is making them wiggle around and they're not communicating with each other necessarily so that they're all lined up periodically. Gabrielle says, when the dopant could be on the A site or the B site based on size, how do you tell experimentally which site is predominantly on? That is an excellent question. And so it's really hard to do directly, but there are ways that you can do it by indirectly and by combining different features, different measurements. So let's go back to this slide so I can talk to the diagram. So let's say we've got a miscellaneous perovskite here, and we want to add something. I'll use PZT, and we're going to throw in a lanthanide. So in PLZT, if that lanthanide is lanthanum is smaller than lead, but it's large enough that it really can't fit very well on the B site. But if we go down the lanthanide series, so if you're familiar with the lanthanide contraction, that means that as we add more and more electrons and protons to the lanthanides and go higher in atomic number, the ionic radius actually shrinks. And so if we're all the way on the lutetium side, lutetium wants to fit just on the B site, and lanthanum wants to fit just on the A site. And that means that somewhere in between there's going to be a lanthanide that is perfectly happy being on either one, equally happy being A site or B site. And because the lanthanides are all 3+, that means that if it sits on the A site, it is a donor dopant, and if it sits on the B site, it's an acceptor dopant. So now we get to go back to our defect chemistry and write out a Kroger Venn diagram saying, all right, let's say it's dysprosium. Dysprosium is pretty close to the middle of the lanthanide series. If I put this dysprosium in and it sits on the B site, that's an acceptor dopant. If I'm acceptor doping my material, I should see more holes instead of electrons. I should see more oxygen vacancy pinning sites, and I should get a little bit harder of a piezoelectric response. If it's sitting on the A site as a donor dopant, then I'm going to have fewer of those oxygen vacancies. We're going to have more mobile, fewer oxygen vacancies pinning domain walls. So I'll have more mobile domain walls, probably have a higher permittivity, might have a little bit higher loss because there might be a few extra electrons hanging out. Those are the kinds of things that we have to go through. You can also look at it by changing the PO2 that you're sintering in or that you're measuring in, and see responses that way. So the first step is, if it, from an ionic radius perspective, it can go on either site, then we say, all right, what would it mean if the valence is the same, but on this side it's a donor and on that side it's an acceptor? It gets more complicated if you have something like tin or bismuth, where technically they can change valence as well as site, and now things get a little bit more complicated. Fortunately, within the PZT system, at least, tin always wants to be on the B site, but it is possible to make tin A site perovskites. They're just hard to stabilize. So hopefully that answers your question, Gabrielle. If not, jumping again, I'll continue trying to explain what we're doing with the relaxers. Along the lines of your question, though, I think we talked a little bit about calcium doping of barium titanate when looking at MLCCs. So calcium is in the same column, it's alkaline, or the same column as barium, but it's much smaller. So when you put calcium in for barium titanate, some of the calcium replaces barium, some of the calcium replaces the titanium. And as a titanium replacement, it is an acceptor, a double charge acceptor. And so that's one of the nice things about those amphoteric dopants, as they're known. They can go on either site. So you can either go on the A site or the B site. Sometimes that just means added chaos and it's hard to know what's going on. Sometimes you can end up with a system that is self-correcting. So it essentially jumps on whichever site is going to minimize the number of extra dopants or extra defects that are present, and ends up self-compensating for other impurities that you might have around. So that's one of the nice contributions of those middle lanthanides, both to PZTs and to barium titanate, is that if they can go on either site, then a lot of times you can end up self-compensating for other unknown impurities, unintended impurities. All right, so back to relaxers. This variation in local bond environment, and the fact that the dipoles associated with each one of these ions in each one of these unit cells does not have a really strong correspondence with or correlation with the unit cell next to it, means that they're not correlated. So in lead titanate, in barium titanate, in normal well-behaved ferroelectrics, if you have a dipole here, then it's very strongly going to influence what happens to the unit cell next to it and the one next to it. So maybe that influence is to make it anti-ferroelectric. Maybe that influence is to make it all point to the same direction and have a large domain, but there's a very strong local influence from one unit cell to the next. In relaxers, that influence is much smaller. it's not as local. So the influence extends over a larger region, but the magnitude of that influence is much, much smaller. And so the way that this is often drawn is with these polar nanoregions. So this happens to be a slightly fancier looking image from relatively recently that I chose, because it's showing that there is correlation among these different regions. And so all of the dipoles in this region are kind of sort of pointing in the same direction, and all the dipoles in that region are kind of sort of pointing in the same direction. But the big difference for relaxers is that these the dotted lines in here that are representing the edge of the polar nanoregion, those are far less well defined than a domain wall in a standard ferroelectric. So these are really dynamic, and they're sort of wiggling all over the place. And there's a large amount of very highly polarizable, but not coherently arranged matrix in between all of these. And so you apply an electric field, and the sizes of these polar nanoregions are going to fluctuate greatly. So they're going to all grow a little bit under a field and then go away. And that requires this dynamic changing of the size of the polar nanoregions happens at a much, much lower field in these relaxer ferroelectrics than in poling a normal ferroelectric. So for example, in a normal ferroelectric, to get any sort of significant change in the domain wall structure, you've got to get all the way out to the coercive field where you get macroscopic switching of these things. The relaxers, you can operate in really low fields way below the electric field and see large changes in the region, in the regions that are sort of somewhat poled, so that they're sort of communicating with one another. So the phrasing that people use for this is actually either as a dipole glass or slushy domain walls, slushy domains. And so you start with a really squishy, highly polarizable matrix, and some of those dipoles are correlated with each other and some of them aren't. And so you end up with, you apply a little bit of electric field and it just nudges them all in the same direction, and you get massive response. That's how we get these huge polarizabilities, huge relative permittivities out of these relaxer materials. That's also where the frequency dependence comes from, because the faster you wiggle the sample, the less time each of these has to respond. And so when you apply a slow field, if you apply it at a low frequency, there's more time for everything to respond. If you apply a large frequency, then they can't keep up quite as well. That's why we get the frequency dispersion that we see. So I mentioned this highly polarizable matrix that also plays out in the strain, and so we'll talk about that in the next couple of slides. But I want to point out what happens with these PMN materials. You can also further engineer that by adding lead titanate. So lead titanate is a really strong, wants to be a normal ferroelectric. You alloy that with PMN. So basically what that means is you just throw titanium in, and you can end up with this PMN PT. So this is a combination of that lead magnesium niobate relaxer with lead titanate, a classic first order, very strong, normal ferroelectric. And when you look at the phase diagram, PMN itself is rhombohedral. Lead titanate is very strongly tetragonal. And then in between, you get this similar to a morphotropic phase boundary that we saw in PZT, but it's a little bit more curved, and it's got a lot more variety happening underneath that curvature. And so this covers 5 mole percent, something like that, 10 mole percent of lead titanate composition space. And then between the rhombohedral and the tetragonal, there's a monoclinic phase, a couple of orthorhombic phases, and all sorts of chaos. In fact, for the PMN and PMN-PT, this is labeled as rhombohedral, and this is labeled as cubic. But it's really, really hard to tell what's going on when there's so much dynamic distortion in these samples. And so if you look at the plot up here where it's showing the macroscopic properties of a relaxer ferroelectric, this is from one of Xujun Zhang's recent papers. At high temperature, everything is cubic, and we can describe that the same way that we describe the paraelectric phase in most other perovskites and high permittivity materials. And as we cool it down, It doesn't follow the Curie-Weiss law, which we talked very briefly about earlier. But then we get into this maximum in permittivity that it corresponds to the structural phase transition. And then we get this region of very high frequency dispersion, but still really high permittivity. From a crystal structure perspective, we know that it's cubic up here. We know that it can't be cubic down here because we can measure all sorts of, we can measure a ferroelectric response, for example, like we see with these. We can measure second harmonic generation that tells us that it has to be non-centrosymmetric. But in this region in the middle, when we do diffraction, X-ray diffraction, electron diffraction, it looks cubic. And that's because all of these little dipoles, each individual dipole is, each individual unit cell is not cubic because there's a spontaneous dipole built in. But they're all pointing all over the place and not correlated with one another. And so when we average that out over the entire X-ray beam or electron beam that we're using to make the measurement, they average out to being cubic. But we know it's not cubic locally because of the properties. So this is often referred to as pseudo-cubic because we're lazy. And that's just a way of cheating and saying that it looks cubic when you measure it, but we know it's not locally. And eventually we get to low enough temperatures where all of these, the vibration and the oscillations of those dipoles go away and they all correlate together, and we get back to a normal looking ferroelectric that we can definitively measure as, say, rhombohedral or tetragonal or whatever the situation is. And so basically what this is showing is that the thermal energy of wiggling things around combined with the heterogeneity and the differences in local bond environments locally give us a lot of disorder and a lot of variation in the local properties that manifest macroscopically as huge relative permittivity and huge strain that goes along with that. So when we apply an electric field to these, we get really, really large strains that come out of these materials. And that's because this highly polarizable matrix is responding very strongly to the field. So we talk about it in terms of relative permittivity. Well, what does that mean? That just means that you're stretching dipoles. When you're stretching dipoles, you're also getting strain. So we're going to take advantage of that field-induced strain in a couple of different ways. And so this is one of the slides that I threw in case you downloaded these earlier. You don't have this one, but it's up there now. And so there are two different components to overall strain that we can get. One is the piezoelectric response, which is what we've been talking about. The other is a quadratic response, which is electrostriction. And so if I skipped over a lot of the math of the Landau, so this is also Landau, in case people are interested in looking it up. So you can describe polarization as just a Taylor expansion. And if anybody hated that portion of Calc 2 as much as me, I try to ignore the Taylor expansion aspect of it. But it's really just saying, even if we don't know what's going on, we can write out an equation that says there's going to be a linear response, a quadratic response, and then a third order, fourth order, and so on and so forth. And from that, because of the symmetry of the material, we can say that the odd ones, the odd components, are going to only exist in non-centrosymmetric materials. So that's why the piezoelectric response that we say only happens in non-centrosymmetric materials, it's linear. So you apply a field and you get a strain. And so when we look at the hysteresis loops, there's locally it's going to be linear because that's you could have nonlinear aspects of it, like the compliance might be nonlinear and you might saturate and these kinds of things. But locally, that piezoelectric response is linear, and because of that, we can get negative strain. So if we have a polarization this way and we apply the electric field opposite that, then the strain is going to be negative. We're actually going to shrink that dipole. Whereas if we apply an electric field along the same direction as the dipole is going to get larger. And so that's what we see in piezoelectricity. The second order effect is known as electrostriction. And this just says that you're going to vary with either the square of the polarization or the square of the field, depending on whether you're talking about direct or converse. So in most materials, this electrorestriction ends up being so small that we don't care, that it's 1% or less, usually far, far less of the contribution to a lot of piezoelectric materials. But for these relaxers and other materials that have a really, really, really high polarizability, really high permittivity, you can actually start to get significant contribution from this quadratic effect. And what that means is that when we apply an electric field, the strain that we get is always positive. So even when we apply a negative field, we still get a positive strain. And so a comparable example of this is magnetostriction. So there's a magnetostrictive effect that's essentially the same as this electrorestrictive effect, but it's when you have a large magnetic field, you get strain. So electrorestriction, electric field strain, magnetostriction, magnetic field strain. And all of you are familiar with this magnetostriction, whether you know it or not. If you've ever walked by a transformer, a power line transformer, and you hear it hum, that hum is vibration from magnetostriction. And because of this fact that the strain is always positive, even though it's in where we apply a negative field or a positive field, because we're applying an oscillating AC field, then we're actually going to hear that hum. In the US, the frequency of the power lines is at 120 hertz. We hear that hum, sorry, it's at 60 hertz. We hear that hum at 120 hertz because we're getting maximum in strain at both the positive and at the negative. And so the frequency that we hear that hum is twice the applied frequency of the current flowing through that transformer. So that's magnetostriction. We can get the exact same thing in these relaxer materials and others, but the relaxers are the ones where the values are large enough to matter. They have really, really large electrorestrictive coefficients here. And so that gives us a contribution to, we get the piezoelectric butterfly loop plus an electrorestrictive loop. And so if you think about that from an application perspective, not having this hysteresis of the butterfly loop might be valuable. So maybe you don't want to have to deal with the uncertainty of that hysteresis of what was its field history. I don't know where it's sitting on its loop to know what kind of strain I'm going to get. With an electrorestrictive material, there is no hysteresis. At least there's no hysteresis to the electrorestrictive portion. But it's also a quadratic effect, so it's not completely linear. So you've got to deal with the fact that when you apply a field, it's the square of the field that's leading to the strain or to the polarization rather than the linear response. So one of the benefits and challenges of dealing with these PMN and related relaxing materials is that now you've got a significant electrorestrictive contribution. What does that mean in terms of strain? Well, here are the world leading PZTs. And here's the amount of strain that we're able to get out of these PMN and PZN based single crystals. So relaxers and relaxer modified relaxer, PMN PT, for example. And so that's a huge increase in the amount of strain, field-induced strain that we can get out of these materials. It has absolutely revolutionized medical ultrasound because these large D coefficients and high coupling coefficients, the coupling coefficients are roughly twice that you can get out of PZT. The strain, as you can see on here, is 10 times what you can get out of PZT. And so these are just massively better piezoelectrics in pretty much any manner that you can describe them because of this relaxer type of response. You'll notice that all of these that I'm plotting on here are single crystals. So it's really, really, really hard to grow single crystals of PZT. But these PMN, PZN type materials are a little bit more amenable to growing single crystals. And so because of that, we can get these much higher quality, much better aligned crystallographically types of samples, and therefore take advantage of these massive, massive strains. So think about that for a second. This is 1% strain in a ceramic. Most ceramics fail well before they get to 0.1% strain. And so part of that means, wow, these single crystals must have no critical flaws in them that are leading to fracture. Another aspect is the elastic modulus is very, very low for a ceramic. So obviously it's still a ceramic. It's still relatively stiff compared to polymers. But for a ceramic, this is really squishy. The elastic modulus is quite low. And that's how you're able to get so much strain. And that also relates to the very high permittivity, because that low modulus means you apply a field and you can get those bonds to stretch a lot. So you've got soft bonds that you can pull apart with that electric field. So the photos on here are examples from CTS and TRS, which are two of the leading companies that grow these single crystals and then use them for medical ultrasound and all sorts of other things. So I've listed a few of the multiple different generations. So PMN and PZN were the originals, and then they've been modified in various different ways. So you can increase the Curie temperature by adding indium. You can decrease the losses by adding manganese. And recently people have found that throwing in samarium in particular, a few of the other lanthanides, you can get another massive increase in the strain that you can get out of these materials. Another 5x, 3x sort of increase in the strain by throwing in a few percent of a lanthanide to help disrupt things even further. All right, so if we're going to make these crystals, then how do we do that? Most of these are done via Bridgman growth. So you may be familiar with Czochralski methods for growing single crystals, or for example, silicon. That doesn't work so well for these complex materials that have may have phase segregation, that don't melt congruently, that have a lot of different cations that you have to get ordered. So generally people end up using Bridgman growth. And just as an example, so this is the phase diagram that I'm showing here is actually for KTN, so it's potassium tantalate, potassium niobate. It's not for PMN or PMN-PT, but a similar phenomenon exists in the PMN systems where you actually end up with a region where if you let's say you wanted to grow 50% composition, if you start with your initial batch that's 50-50 and hang out here, you're actually going to end up growing a solid that's depending on what temperature you're at, you're going to grow any region of these solids as your crystal that precipitates out. And so to do this kind of growth, you have to know the phase diagram really well and have a lot of control over the chemistry of your sample in the process. Happy to go into more detail on the way that this single crystal growth works, and the fact that you do get a little bit of chemical segregation, and therefore you get a change in composition through the thickness of your crystal. But TRS and CTS have done a great job of developing these technologies over the years to minimize that chemical segregation. It's still not zero, so when they grow one of these crystals, they have to chop off the top and bottom and measure where they are in between to get certain properties. But as you may have seen from the phase diagram, there's a wide region of a morphotopic phase boundary type region in here that can be useful, just slightly different properties and therefore slightly different ideal applications for each of them. Another approach to getting single crystal-like properties, but getting the advantages of making a ceramic, a polycrystalline ceramic, is this templated grain growth, or single crystal conversion is an older name for it. So this is basically Ostwald ripening and grain ripening gone mad. So you start with a single crystal. In this case, there's just a single crystal sitting on top of a polycrystalline bulk ceramic, and then you heat it up and let ripening take over. So big grains like to eat little grains. The whole driving force for sintering and for grain growth is to minimize the surface energy, the free energy of grain boundaries and exposed spaces. And so the extreme version of this is you're going to want to turn that polycrystalline sample into one single crystal. And so from that single crystal template, you can grow into the polycrystalline matrix and convert that polycrystalline ceramic into a single crystal. So ideally, this allows you to get the crystallographic orientation that you want from a single crystal, but the ease of fabrication, for the most part, of a powder-based ceramic. So ceramics are great in that they're usually a little bit tougher than the single crystals. You can make them generally a lot cheaper than by growing a single crystal. It allows you to have a little bit more flexibility in terms of geometry and all sorts of fun stuff. But you may not get the properties that you really want, that you can maximize with a single crystal. So another approach, instead of just throwing a single crystal on top of a polycrystalline bed, is to do what is known as templated grain growth. So you start with platelets. Each platelet is a single crystal. And then you use something like tape casting that has a high shear to align those platelets. And that gets all the crystallographic directions, at least for the thin direction, pointed in the same area. And then you just go through the same ripening process for each one of those platelets. So each one of those platelets grows into the matrix around it, and you end up with a polycrystalline ceramic that has a net crystallographic texture that mimics that of the single crystal. So really cool techniques. There are a bunch of challenges along the way, but it's one approach to getting some of the advantages of the single crystal with the improved properties, but also some of the advantages of the polycrystalline ceramic. And there are absolutely limitations to the geometry. It all depends on, so this example up here, the reason it's growing this direction is because these faces end up being the lowest energy plane. And so you can, by changing the direction of your seed, you can change the growth rate and the eventual shape of the crystal that you end up with. A lot of the challenges that remain in this templated grain growth approach. So from a geometric perspective, the biggest challenge is, how do you use shear to align the platelets? Or maybe you can use a magnetic field, or you can use some other way to get the texture of the platelets in the first place. And then you have to be able to grow from that dense platelet into a porous matrix. So best case scenario, you've packed your packing density around those platelets is 50%. And so now you have to get the matrix, the polycrystal matrix around it, to center on top of these dense platelets and shrink by 50%, and then take over the texture, the crystallographic texture of the platelets without fracturing everything because of that stress associated with a 50% shrinkage. So the classic challenges of ceramic processing made even harder by that texture. So they're great R&D techniques. They are being commercialized in a few niche places so far, but a lot of additional possibility there. When you really need the additional properties, the improvement in properties that you can get by having the crystallographic texture of a single crystal. All right, we'll come back to optics and wrap things up on Thursday. I don't have time to jump into that one now, but please shoot me any emails that you have, any questions that you have via email, and look forward to seeing everybody on Thursday. Thanks.
Thank you, Jim.